extend my welcome to Dr. Neelesh Shukla, sir.
This call is now being recorded.
Are you there, sir?
Yes, I'm here.
Neelesh Shukla, sir. Dr. Neelesh Shukla.
Yes,
So,
I'm here, sir.
this is the eighth session, day 4, second session, and overall 6-day ATAL FDP. Fourth day is going on, and Shukla sir is here with us. One more industry person, and as a coordinator of this FDP, I welcome Dr. Neelesh Bharti Shukla. Welcome, sir.
Thank you, sir.
Uh, I'm delighted to introduce you for the sake of all the participants from various states of India. Dr. Neelesh Bharti Shukla, a highly accomplished expert in polymer engineering and sustainable technology. Originally from a small town in Madhya Pradesh, Dr. Shukla discovered his passion for polymer during his BTech in polymer engineering at Amruta School of Engineering, Coimbatore. He deepened this passion of polymer during his PhD at Indian Institute of Science, ISC, Bangalore, where he worked on superabsorbent polymers under the guidance of Professor Giridhar Madras, earning his doctorate in 2012. Dr. Shukla's professional journey is marked by excellence and innovation. He was recruited by Aditya Birla Group directly from the ISC and spent 12 years at their corporate R&D center in Navi Mumbai, driving product and technology development in fibers, textiles, and sustainable packaging. Currently, he leads a technology platform on sustainable polymers at the Dover Corporation's corporate R&D center in Bangalore, where he continues to develop cutting-edge solutions in polymer science. Dr. Shukla's dedication to advancing sustainable materials and his lifelong commitment to learning make him an inspiring figure. We are honored to have him with us today to share his insights and expertise. So please join me in welcoming Dr. Neelesh Bharti Shukla. His topic of today's talk will be high performance polymers. Thank you, sir. Welcome once again, and you can start your session. Your co-host, you can share your screen, sir.
Thank you very much, Dr. Patil, for your introduction. It's a pleasure to be here to share some learnings that I have had over more than a decade now working on polymers. So I'm happy to be here and talk about high performance polymers. Give me 1 minute. Is my screen visible?
Yes, sir. Yes.
Good evening, everyone. And
Good evening,
and
sir.
today I'm here to talk to you about high performance polymers and their applications. So before we delve deeper into this very interesting topic, I would like to set the outline of my presentation. So I have tried to divide my presentation in two parts. The first part would be spent in developing some understanding about polymers, and this is required as I understand we have people from various different backgrounds. Not everyone might be aware about the polymers to a great extent. So that's where we'll spend some time to understand about the polymers. And then in this section, I will introduce you to polymers. I would talk to you about to kind of set context for what are these high performance polymers. I'll also try to give you some flavor about the global developments or perspectives on high performance polymers. And then we would go to a very special or very interesting aspect of polymer science and engineering, that is understanding the relationship between the polymer structure and its properties, and that holds the key to identify a suitable material for any given application. So from my entire session, if I want you to take one thing away today with you, so that is develop the understanding about the polymer structure and property, and that would help you identify the kind of materials you're looking for any application. So that will be the foundation we'll build, and on top of that we'll delve into high performance polymers and their applications. So towards the end, I'll try to summarize what I talked about in this presentation, and we can have questions and answers. But if you have any question in between, you can please unmute yourself and do ask the questions. So before I begin our journey about polymers, so I would like to understand from you, how many of you have heard the word polymer before? So are you aware of the polymer? Just want to gauge the level of knowledge or familiarity with the topic. Is there anyone who has not heard the word polymer? That would be an easier way to go.
I don't think anyone is there who has not heard the word polymer.
Great, that's great. Very good. So obviously, the kind of developments that have taken place in field of polymers, or what we generally call them plastics, and it's impossible to live our lives without plastics. So we are all aware of that. So that's where you have come across many polymers from the morning to night, and we'll try to identify what all high performance polymers are also there, which might not be very evident to us, but we do use them directly or indirectly. So that's what we'll try to see throughout this presentation. So coming to introducing polymers very briefly. So polymer is comes from the Greek words poly and meros, a combination of these two. Poly means many and meros means parts. So that's how the word polymer has been made. It's also known as macromolecules. So because these polymer molecules are very different than the regular chemicals or small molecules what you would see, these are much longer molecules. Now, how are polymers made? So if you so this is a polymer, and in order to make a polymer you need something known as a monomer. So monomer is a smaller molecule, and polymer is a much longer chain of these monomers linked together. So this is a polymer, and here you have got a monomer. Now, one polymer that we all have used widely and we have seen it everywhere, it is used to make the polythene bags, the shampoo bottles that we use in the bathroom, the toys with which our kids play, and even some of the safety equipment that is worn by people in army and very dangerous situations. So this polymer is a polyethylene. It's one of the simplest polymer to start with, and you start with a monomer named is ethylene or ethene, and you polymerize it. The polymerization means just joining together of these small molecules in a chain, the way you'll make a garland using small flowers. That's the way the polymerization is done. And now this polyethylene is one of the most popular plastic in the world. So you just take ethylene and keep on adding hundreds to thousands of these molecules together and get a long chain molecule, and you call it a polymer. So these are synthetic polymers. Synthetic polymers are those polymers which are being synthesized by man using the chemicals that are available, or they have been produced by different processes. But nature, so man has learned to make these polymers in like last 100 years or so, 100, 150 years or so. But nature has been making polymers for us for much longer than that. So if you look at silk, wool, our own DNA, or the cellulose that we get from the trees, or the proteins. So these are all of these are also polymers, and they are known as natural polymers. So you can broadly categorize polymers in synthetic polymers or natural polymers based on the kind of origin they have, the kind of the roots they are made by. There are many more other ways also, but we'll just stick to this for time being. Now, I understand there's a different level of familiarity with polymers. So I've just tried to capture some of the resources which would be useful even after today's session. So try to grasp what you can grasp today. But if you are a beginner and you have not too much into polymers or chemistry so far, I would request you to visit the Macro Galleria site. Its link is also provided below. And this is a very fun way to learn about polymers. And they also have a separate section about it, Kids Macro Galleria. So even kids or people who are in school, they can also try to learn about polymers in a very fun way. So this is about the beginners and those who are advanced learners. So few books which I have found very, very interesting and informative throughout my career. They have listed here. So one of the best book that I came across was The Principles of Polymer Chemistry. This is by the Nobel Prize winner of 1974, Dr. Paul J. Flory. And apart from that book, there is one more about Principles of Polymerization by George Odian, and another one by Bill Mayer. That's a textbook of polymer science. So these are highly recommended books for anyone who wants to learn more about polymers. So with that bit of information, I would like to now introduce you to high performance polymers. So if you look at polymers, they have different properties, different characteristics, and the way they have been used in general, the kind of volumes they have, the kind of properties they have, that has been used to categorize them. So we talked about one categorization, natural and synthetic, that was based on the origin of the molecules. This other categorization is based on their performance. So here you break the polymers into 3 or 4 levels. So generally, earlier it used to be called commodity plastics, which are very basic polymers we generally use day to day: polyethylene, polypropylene, PVC, polystyrene. These are the materials. So these are they don't perform they don't have very high performance characteristics. They are used for non-critical kind of applications. Above them, one level up, are engineering polymers. So these polymers are something which have improved properties over the commodity polymers. So if you look at these polymers, you will find that their chemical resistance is better than the commodity polymers. Their general mechanical properties will be also better than those of the commodity plastics. One level above them will be high performance polymers. So earlier altogether they used to be called specialty polymers. Now, as more and more developments are coming, new polymers are getting introduced, people have started classifying them as high performance polymers and ultra high performance polymers. But for our purpose, let's just put them together. All of these top two levels of pyramid are combinedly called high performance polymers. So how these polymers are different than the other two categories? These polymers have got much higher thermal stability, so they can be used under higher temperatures where the earlier two categories cannot be used. They have got better chemical resistance than the other two categories, and some specific cases are there where these materials have low friction properties and very good wear kind of properties. So that's what differentiates these polymers from the other polymers. So overall, if you want to define high performance polymers, so these are the polymers which would retain their desirable properties even when you are exposing them to very harsh conditions. The conditions could be very corrosive chemical environment, very high temperatures, or very high pressures. So that's the way these are defined. Another way to look at polymers is one more way: amorphous and semi-crystalline. We'll touch upon this aspect slightly later on in the presentation. Now, if you look at the overall production of plastics in general, so the data says that in around year 2023, more than 400 million tons of plastics were produced globally. Now, if you look at the pyramid, so you don't know that's the whole pyramid. If you just want to understand what was the contribution of high performance polymers, it was very, very small. So only less than 1% volume is high performance polymers. So they are very niche kind of segment among the polymers, but they are extremely valuable. So if you look at again 2023 data, roughly 25 billion USD was the market of these polymers that time, and it is growing at a very steady rate of 9.2% CAGR, and it's expected to be touching 55 billion USD by 2020 2032. So that's what tells you that there's a lot of growth taking place, new applications are coming in, and as we are always on to use better and better materials for comfort, safety, and enhanced performance, they will find more and more applications. So talking about the applications, so in general, they go for many transportation related applications, be it automotive or aerospace. They are used in electrical and electronics kind of industries. In industrial applications, they go for making many equipments which handle chemicals, and in chemical industry, a lot of these are used. In medical field also, they are used to make many devices for treatment, even implants, and a lot of them are used to make the drugs in the pharmaceutical industry as well. And then there are some other applications. Now, as one aspect that I missed on, as you go up the pyramid, the cost is increasing. Sorry, the performance improves as you go up and up the pyramid, but at the same time, the cost of these materials also increase, because commodity plastics are generally not that they don't require very sophisticated molecules or equipments or processes to convert them into polymer. On the other hand, the ultra high performance or high performance polymers, they need very stringent kind of conditions to carry out the polymerization. They need the very specialized equipment to convert the polymer into useful product. So that's what. And additionally, it's all about scale. The scale, as I used have seen, is less than 1% of the total. So that also pushes their cost up. So they are generally costlier as compared to other materials. And you would see in just roughly, if you want to understand the ballpark number for the price, so they would cost you somewhere from $10 to $100 per kg. So that's the economic part of the high performance polymers. Now there are many uh, manufacturers across the globe who make different kind of high performance polymers. So Saint Gobain, Solvay, Victrex, DuPont, Daikin, Sebec, BASF, these are the companies, even 3M, Celanese. Some of these are some of the key manufacturers. The list is not limited to this. There are many more, but for your reference, some of them I have listed here. So all this information that I'm sharing on each slide is available freely. So there's nothing, no copyright material here that comes from any organization. So you can click on the link below here, and you can try to learn more about whatever is presented on this slide. Now, when you talk about high performance polymers, so these are few examples of high performance polymers. So for example, PEEK. PEEK is one polymer which has got very good strength and thermal stability. And then these properties make it suitable for applications where you need strong mechanical properties and high temperatures. Now, the PSU, polysulfones, they have got very good electrical insulation, very good mechanical strength, and they are very good in terms of their dimensional stability also. So for these properties, they go in the electronic industry. Polyphenylene sulfide, PPS, this polymer has got very good purity and very good chemical resistance. Obviously, mechanical strength is also very high. So these characteristics make it very suitable for medical applications, and also electronic and automotive industry. Another polymer, polyphenylene sulfone, which has very good impact strength and chemical resistance. So this polymer, based on this structure, it can withstand the steam sterilization, and that makes it very suitable material for medical application. We have polyether amide, again having very good strength and good electrical insulation, and additionally good radiation and chemical resistance. So these things make it very suitable for electronic and aerospace applications. We have couple of fluoropolymers, PTFE and PVDF, and these polymers are very good. They will have very good chemical resistance. They will not have very high mechanical strength, but their chemical resistance is something that makes them very useful, and that's where they are widely used in the chemical industry. So as you can see on this slide, this you can see on this slide, I have put many polymers, their properties and their application. So there's a link between the polymer and their properties. So the properties of any polymer would depend on what kind of chemical structure it has. So that would the basic chemical structure, the what kind of chemical constituents are there, the monomers or the repeat units that the polymer has, which make it, they would determine to a large extent the properties of that particular polymer. And then subsequently there are processing is required to convert this polymer from raw material to a shaped shape or product form, and that would determine the application. So in order to understand the proper to be able to identify a suitable right material for any particular application, one needs to understand the relationship between the polymer structure and its properties. So that's what we'll do. We'll take few cases here and try to understand that aspect before we move further. So as I mentioned in earlier slide, so these four aspects, the structure of the polymer, the properties of the polymer, their performance, and their processing are related. So you have to have all these, and one aspect that is missing is cost. That's the economics of the whole thing. These four, and then plus one factor, when they all come in together, they are coordinated. Then you have a proper material converted from the raw material to a final product, which can be useful for the society. Now, if you talk about structure, so as you are, most of you should be aware about polymers, as I mentioned, they are long chain molecules, but those long chains can be in very different ways. They can be linear, they can be branched, or they can be cross-linked. These chains can be very flexible, or they could be very rigid. Then, as I showed you one example, we had polyethylene coming from one monomer ethylene. You can use monomers, more than one monomer, and you can end up with copolymers are something where you have used more than one monomer and they have copolymerized. Or you could use polymers in combination, which is also a property. You have need some you have polymer A with certain property, polymer B with certain property, you mix them in a suitable ratio, and you got a third material which has the properties of both. So that's called polymer blending. Beyond that also, the polymer structure or the chains, the way they arrange within the structure gives rise to amorphous and crystalline regions, and there's something known as LCP, liquid crystalline polymers also. So these are the aspects which define the structure of the polymer, and eventually the these things would determine these particular structural parameters would determine the properties. When you talk about polymers, there's something very unique feature about the polymer: its molecular weight, then its mechanical strength, its thermal characteristics, its electrical insulation properties, its tribological properties. That means how does it wear and what kind of frictional properties it has, and obviously their chemical compatibility. Now, once you have got hold of structure and property, you might have some idea about the materials, few materials you would have selected, but will you be able to convert them into the shape that you want to use in the final product? So that's where the processing aspect of polymers comes. So polymer processing is entirely a big area separately. We are not going to cover too much about it, but basically, what are the processes that are required to convert a raw material into a suitable product? So that's where you have limitations. Some of the products can be melted and processed like thermoplastics. So there are different methods for that. Some of the them are thermoset material. They will not flow. So you can't use this kind of process for that. You have to go for something else. And then again, if you want to make something like long fibrous things, you have to go for a spinning kind of process, which is generally used to make fibers like polyester or nylon. Some other places you have to do molding, blow molding kind of thing, and roto molding. So depending on the shape and size of your product, you might, and obviously polymer properties, you choose a process that converts it to the final product. And obviously performance is something that applies the filter. So what kind of industry I'm talking about, what are the operating conditions in that industry, how long my material has to be performing, what kind of chemicals it will come across, will it be exposed in sun, what kind of temperature will it be having, will it go to high temperatures or low temperatures. So these are the performance characteristics which demand the selection of the right polymer. So I hope I have, so this is the one aspect that is very critical, and let's look at few examples of how the structure is going to affect the polymer property. So there's some phenomena, as you know, if you take water and cool it down, will convert into ice, the solid phase. If you heat it further from room temperature to higher temperature, it will evaporate. So those are the thermal transitions that water undergoes as you change the temperature. So polymers also undergo this kind of transitions, but polymers are more complicated than low molecular weight molecules such as water. So as I mentioned, the polymers have got very long chains, and these long chains can be present in various kind of arrangements. So if the polymer chains, which are very long, are arranged, they fold onto each other and they are neatly arranged in this packet, this kind of form, they are known as crystalline. The polymer would be known as crystalline. On the other hand, if you have these chains going everywhere, randomly going in and out, you would have something known as amorphous. But most of the polymers generally fall in the category of semi-crystalline. So they are not many polymer, or very few would you can call them completely crystalline. Otherwise, most of them come as semi-crystalline, and there are elastomers and thermosets which would be called amorphous. So these two characteristics are there. Now, what kind of transitions take place in polymer? There are two main transitions. One is your glass transition temperature, and second is your melting temperature. Melting temperature is very easy to understand. The way ice melts when you heat it, or anything else will melt. Any metal will also melt when above its melting temperature. The polymers will also melt, but only the thermoplastic polymers. Thermoplastic polymers are something which can be heated. Once you heat them from solid, they will convert to liquid and start flowing. So at melting point, you will have a transition from solid to liquid state, and this uh, transition temperature relates to the crystalline regions of the polymer. And here the polymer chains start moving relative to each other, and you get liquid like motion. On the other hand, glass transition temperature is something where polymer changes from a glassy to soft rubbery stage. So this pertains to the amorphous state. So what happens here? This is generally Tg is lower than Tm. What you can see here also, the Tg is lower than Tm. And when you cross Tg, suppose you're increasing the temperature, you cross the Tg, material will not start flowing. You will not see any change, phase change the way you will see at Tm. What will happen? Only some short chain movement will start. So enough energy is provided where some segments of these polymer chains, they start to move. So there will be short range movement. But what happens because of this? This will disturb structure to some extent. So that's where the if you increase the temperature, the mechanical properties of the polymers get affected significantly. So when polymers are below the Tg, they have more or less kind of same level of strength. Once you cross Tg, the state changes from a glassy state to a rubbery state, softer state, and that's where a loss in modulus is observed. So properties drop significantly once you cross Tg. And as you go further, you keep on increasing the temperature. If a polymer is semi-crystalline, in that case, it will start melting, because at the height and at Tm, the semi-crystalline domains would melt, and again, there will not be any more strength, and the polymer will start to flow. On the other hand, in case of amorphous polymers, there are no crystalline domains. So you will see a very sharp or very low kind of TM, which not even be available. Crossing polymers, they cannot have the relative motion, which happens in the case of uh, crystalline polymers. So they will not be showing any TM. Yeah, so that's the way the properties depend on the structure. And then any polymer, how one polymer will be amorphous or semi-crystalline depends on its chemical structure. So as we saw that the properties depend on the temperature of the polymer, and there are transitions as you go from low temperature to high temperature, so they affect the performance of any polymer. So you can look at this this curve. So this is a typical thermogravimetric analysis, which TGA curve. So you can see generally what is done, a polymer is taken and it's subjected to a heating rate from room temperature to any high temperature, and the way the material will go from Tg and to Tm to further higher temperatures, most of these polymers are organic polymers, and they would start to degrade at certain point of time. And at what temperature this kind of degradation would take place depends on their structure again. So generally the polymers which will have higher degree of crystallinity will degrade at a higher temperature. Polymers which have got which whose repeat units have got aromatic groups and halogens, they will again be having better thermal stability. And obviously polymers which have got cross-linking or they have some kind of secondary bonds like hydrogen bonding or van der Waals forces, they will also be more stable as compared to the other polymers. So these factors are something which push the thermal stability of polymers to a higher level. On the curve here on this graph on the right side, I've tried to compare the mechanical strength and the heat deflection temperature. So you can again see all the polymers based on their structure, sorry, will be having very different strengths. And as higher performance for high performance polymers like PBI, PI, they would have higher tensile strength and even higher heat deflection temperature will be higher. So they can be used at higher temperatures because other polymers would lose their strength at those temperatures. Talking further about the mechanical strength of the polymers, so it depends on one very critical factor, as I mentioned earlier, the molecular weight of the polymer. So as you start taking small molecules, joining them together via polymerization into a longer chain, there's a certain threshold limit up to which the polymer would not have any useful mechanical strength. And after you have linked a certain number of polymer chains, which would vary from polymer to polymer, the material would start showing some kind of tensile strength, which can be of use. But while the tensile strength is increasing, there's one more phenomena that is also taking place. The melt viscosity of the polymer also keeps on increasing with the increase in the molecular weight or the chain length. So the downside is that you have to have if you want very high performing polymer, very high strength polymers, you can keep on adding the more and more polymer chains, but your viscosity would increase, and that would have a counter effect in terms of processing. You would have to reach to higher and higher temperatures. And then there are some polymers where, although they are not thermosetting, but their large molecular weight makes it very difficult for them to be melted and processed. So one such polymer is ultra high molecular weight polyethylene. It's you can say brother sister of polyethylene, which is the simplest polymer, but the number of polymer chains is many more as compared to normal polyethylene, HDPE, LDPE. So that's where the secondary forces come in picture, and they give it very good strength, better strength as compared to uh, polyethylene, but they also increase its viscosity very high, so you just can't easily process it into any article very easily the way you could do with HDPE or LDPE. So you need specialized equipment, and you have to make them by method, and then most of the time you end up doing machining. So you make a block and then you machine it to desired kind of shapes. So that's the impact of the molecular structure in terms of molecular weight on the mechanical strength. Again, the molecular structure would also determine whether your polymer would be brittle, it will be ductile, or it will be highly elastic. And these three category of polymers would certainly behave very differently when you look at their strength in terms of mechanical property. One more example I can show you, there's polypropylene and polyethylene terephthalate. So this is PP and this is PET. Now, if you see, polypropylene has got a flexible chain. On the other hand, the PET repeat unit has got a benzene ring, which makes it slightly rigid as compared to the PP. Moreover, it has got these polar groups as well, which will increase the interaction between the polymer chains. So as a result of these structural changes, the properties are very different. So if you look at the density of polypropylene, it is lower than that of the PET. Its melting temperature is also lower, and its tensile properties are also lower. So that's how what I've been trying to tell you is that the way you uh, play with the structure of a polymer affects its mechanical properties. Now coming to another critical aspect that again relates to the chemical resistance of polymers is their structure. So when you want to use a polymer in contact with any environment where chemicals are present, there are certain factors which would affect its stability, whether it can be a right material or not, or it will work there or not. So first of all, the polymer structure, as I mentioned earlier, the type of chemical that you're going to use, the concentration of chemical, whether you are very using concentrated acids or alkaline material, or they are in the low concentration, temperatures, low temperature, high temperature, or sub-zero temperatures, how long the chemical is going to be in contact with the material, and during the application, are there going to be some stresses on the material, because that will be additional burden on the polymer. So these are the factors which would affect the performance of any polymer under the applications. Sorry, under the environment. Now, generally, if you look at the different kind of high performance polymers, fluorinated materials which have got a carbon fluorine bond, PTFE or Teflon, which we all know is one such material. So this carbon fluorine bond is the strongest bond in the organic chemistry. Additionally, the fluorine is very highly electronegative, and as a result of these effects, the fluorine atoms which are around the carbon chain backbone, they kind of shield the carbon chain from the attacks by these chemicals. So PTFE turns out to be one of the best material when it comes to the chemical resistance, and you can see a wide range of chemicals have been listed in the first column: acids, bases, organics, chemicals and all. So you will not, you can look, you will have access to this later, but you can easily see it. Not There's no other material as good as PTFE. PVDF also comes close to it, again because of having fluorinated atoms in it. So that's the way it is. Again, the way you modified the structure, there's very little difference between polyethylene and polytetrafluoroethylene. All that you have done, you have taken the hydrogen atom from polyethylene, all four of them, and replaced them with a fluorine. And that's the way you have got entirely new polymer with entirely different properties, which are very, very useful for our industry applications. So that's what I've been trying to do so far. I've tried to tell you that how the structure is important to determine the properties. Now we'll move towards the next part of this presentation, where we'll look at some high performance polymers and their applications. So here the structure will not go through the kind of outline that was laid down there. We'll just we'll be moving from very fluidly. We'll be moving from the polymers to applications and vice versa. So let me introduce you to one of the very high performing polymer. Is the family name of polymers known as PAEK. It is known as polyacryl ether ketones, PAEK. So how these polymers are made? Again, you have monomers which will have three different functionalities in them. You will have aryl, basically the benzene kind of rings will be there. You will have a flexible group ether, and you will have a ketone group also, which would give you some dipolar and interactions between the polymer chains. So these three aspects are used to synthesize polymers. Now if you consider this PAEK family, you will have more than around 340 known polymers are available. And how those polymers are made? They are made by changing the order of these, using them in different number, changing the order, and changing the kind of materials from which these groups can be added to the polymer. So we'll not go into all 340 of them today. We'll just look at three different materials today. So you look at PEEK. PEEK would be polyether ether ketone. So they're poly. So this is ether ketone. Okay. Second one is PEK, polyether ketone. So you have one ether and one ketone in the repeat unit. And this is a very longer name. So you have got ether ketone, ether ketone, ketone. PEKEKK. So these three materials are available as polymers from Victrex and different grades. And what you can see here, that the way you change again the ratio of these ether and ketone groups. So if you look at peak, which will have more number of ketone groups, sorry, less number of ketone groups than the ether groups, then PEK, where you have them in the equal number, and then PEKEKK, where you have more ketone groups. So this is the way their structures are different, and that affects their, again, thermal properties. So if you look at the glass transition temperature of these materials, as you go on increasing the ketone groups, keeping the ether ratio, ether groups same, you see increase in the glass transition temperature. And similarly, you can see the tensile strength, sorry, the melting temperature also increases. So again, one more example of, again, connecting structure with the properties of the polymer. Now, why is PEEK a specialty polymer? It's a specialty polymer because it has got very high heat resistance, that again comes from the presence of these uh, benzene rings in the backbone. So it can be used to, you can use continuously to as high as 260 degrees Celsius temperature, and that's very impressive temperature. And it is also reactive, it is also unreactive to many aggressive chemicals. Obviously, not as good as PTFE, because PTFE is the gold standard when it comes to chemical uh, chemical resistance. But this is also very good material, certainly better than engineering and commodity polymers. It has got very good mechanical strength and stiffness, and it can it can resist combustion up to 600 degrees Celsius. So there are materials which will not burn up to 600 degrees Celsius, organic materials. And more importantly, it is a thermoplastic material, so which makes it more, first of all, easy to process into useful products. And after the product life is over, you can still recycle them and reprocess them into the materials, and you can create kind of sustainable cycle using these kind of high performance polymers. So PAEK family, as I mentioned, they have like more than 340 known polymers available in literature. Only few of them have been commercialized and been found to be of use, full application, and some of them are the semi-crystalline, and yeah, most of them are semi-crystalline which have been used. Very few are there which will be amorphous. Now, looking at how do we use this particular high performance polymer. So this PAEK family polymers are used for one special application which everyone talks about these days, that is additive manufacturing or 3D printing. So it allows you to have great freedom to have very short time you can take from the lab to market. You can have very, so it's more useful when you got a very high cost, high value part, but not in very large volume. So that's where you can improve the economics of your production processes. And peak being the high performance polymer, so it is better option than trying anything like polyamide and other PLA kind of materials which are typically used for the 3D printing kind of applications. So you, by using this high performance polymer, one gets stronger parts, and this also has some kind of improved printing over the other materials. So the kind of set, that kind of process you will set would depend on its melting temperatures and all that. So it will require high temperature because peak will melt at 303 degrees Celsius or something. So you will have to use about that temperature. So equipment has to be equipped with that. But you will be able to print very complicated parts which are very good in terms of mechanical strength, and they have got very good chemical resistance as well. So that's one critical example where poly aryl ether ketones are used. The second polymer is sulfone polymers, also known as polyaryl sulfones. Now you will understand that the aryl word aryl would mean that there is going to be a benzene ring somewhere in the polymer chain, and sulfones is SOO group will be also present. So once again, you can vary the introduce ether and make ether sulfones. You can remove them also, and you can have more of rings, funneling rings, and that's the way you can keep on varying the structure of the polymer, and similarly they will have impact on the properties. Now poly sulfones are different from PAEK in terms of that was a semi-crystalline kind of polymer, and sulfones are amorphous polymers, so they will have a transparency which makes them very suitable for various applications, which we'll see in the next slide. So being a high performance polymer, again, good strength and electrical properties would be there. Additionally, this is a very good polymer when it comes to having its resistance to strong disinfectants. And so very many cleaning agents and disinfectants are used in medical industry, and that's this being resistant to them makes it a suitable candidate for that application. It can be used to as high temperatures as 180 degrees Celsius, and it has also got very high hydrolysis resistance, so that makes it suitable for the repeated steam sterilization, making a good choice for pharmaceutical or medical applications. So there are some companies, BASF, Sabic, Solvay, Sumitomo, who make these kind of materials, and as I mentioned earlier, their capacities are not very high, although this is very old data, but I don't think that it would have changed by orders of magnitudes. It would have been at the most doubled or would have stayed in the same kind of range. Now, if you talk about the applications, so polysulfones are used in automotive industry, where being amorphous polymers and using their transparency, they are used to make the housings for the headlamps, because headlamps, the older halogen ones, can get heated up to very high temperatures, 180, 200 degrees Celsius. So that's where these housings with their dimensional stability, good resistance to moisture, and low coefficient of thermal expansion offer a good solution for the housings for the headlamp reflectors. Apart from the automotive engineering, you can find them in your bathrooms and your kitchens. So if you look at a coffee machine, again, many times you'll see that the new coffee machines have the function to add hot steam. So, and they will have to be some of the components which are used, they might be getting washed in the dishwasher and all also. So that's where the hydrolysis resistance is very, very important. And obviously the high temperatures and resistance to detergents. And apart from these, you also have to have the materials which can be used along with the food contact. So these properties make it very good material for some parts of the coffee machine. Similarly, this property of food grade being a food grade material and ability to be sterilized at high temperatures makes it very good material for the baby bottles. Now, looking at the electronics and electric industry, here you have many circuit breakers where latches are made, because these components, they don't stress crack very easily. They have very high impact strength also and very good dimensional stability. So that makes them suitable material for many components used in the electrical and electronics industry. Coming to high kind of application, so not high, very relevant application, water purification. That's where polysulfone based membranes are used for micro and ultrafiltration, because these are some materials which can be precipitated as filaments or films from the solvents, and they have got very highly reproducible porosity. So that makes them suitable material for water purification. Already talked about the medical applications because of their sterilizability and resistance to infectants. So we talked two polymers, PAEK and polysulfones. So these polymers were, first polymer was semi-crystalline, second polymer was amorphous. Now we look at some different kind of polymers which are liquid crystal polymers. So liquid crystal polymers have got some polymer chains which are very stiff, and the beauty is that so if you look at a normal semi-crystalline polymer, it will have ordered change arrangement in its solid state, and once you take it above its melting temperature, the chains will lose their order and they would become irregular shaped. So you can look at, just think of it as like a Maggie packet. So this is the Maggie cake that you take out of your packet, and this is the one that is ready after the cooking has been done. On the other hand, LCPs are very different. So they will have order in their solid state before their melting temperature, and even after melting, they maintain their order. So that's the unique property that they have, and that makes them suitable material for many applications, gives them high strength, and even they can be used to replace metallic components in certain applications. So one application that I have tried to capture here, this comes from a company named as Juice. And what they have done, so they are, if I'm not wrong, they make catheters for the uh, vascular kind of applications. And these catheters have to be MRI compatible. And if you use metals such as SS, that compatibility you cannot match. So that's where the having the properties, good properties, and being able to perform along with the MRI makes these materials very good. So you have got a PTFE based mineral inside there, and on top of that you have got another PTFE layer, and on top of that you have to do the reinforcement by braiding. Braiding is just like covering it with fiber. So this is the braided catheter you can see, and that's where this kind of polymer is used for this application. So that's where the LCPs are different as compared to your amorphous and crystalline polymers, and they are different properties, and along with the strength that they have got, make them even very good materials to replace metals in certain applications. Another two very important materials are aromatic polyamides. So you know polyamides like nylons, which are so any polyamide would have an amide group, that is C double bond O NH. The conventional nylons or polyamides, nylon 6 or nylon 66, would have the linear chains attached to this functional group. On the other hand, the aromatic polyamides, as the name suggests, will have the aromatic rings attached to this functional group, and they can be two kind of main aramides are there. Because of being aromatic and amide, they are known as aramide. So based on the position of the functional group on this benzene ring, they are either para or they are meta. So this just position also makes them very different properties, gives them very different properties. So both are very high specialty fibers, Kevlar and Nomex. They are from DuPont. So DuPont makes them. The para aramid is Kevlar and the meta aramid is Nomex. Both of them have got very good heat resistance, and this comes from their interchain bonds and the presence of these the benzene rings in them. Kevlar is something that you must have heard about. It is used for the protection against the ballistics cut puncture resistance. Basically, you can make a vest which is bulletproof using Kevlar. And the Nomex is a very good material. It's a flame retardant material, and a lot of times many space suits and firefighting gear, all of them are also made from the Nomex. Now, if you look at the properties of the aromatic polyamides as compared to the nylon, you can see the difference, how the properties improve because of the presence of these aromatic chains in them. So you can look at the tenacity, which tells the tensile strength of a fiber. It is almost 3 times as compared to nylon. And because it loses its elongation, it's not as elastic as nylon, because now you have got the stiffer chains present there, but its specific strength has gone up, and its decomposition temperature has also gone up significantly, making it very suitable, like more 400 degrees Celsius plus temperatures it can be used. So personal protection PPEs is one area where both of these materials are used. They're also used in automotive, aerospace, and life protection kind of applications. Going to the next material, which is again kind of liquid crystal polymer. It's Vectra MT LCP. This polymer is used for medical applications, where you want to make a very small thin kind of parts. So you can look at nowadays these wearables are coming into picture a lot more and more. People want to wear sensors on their bodies which can track their health throughout. So this is one such example where you can see a sensor has been placed on the arm. And challenge is, if you want to make something like this with materials, they have to fill very thin walls, and that's where many polymers fail, because they can't flow fast enough under very thin kind of walls. So that's where this particular LCP has been developed, which has 30% glass fiber. Still, it can flow at a very fast rate and fill these small cavities to give you the desired kind of stiffness or the properties that are required for very thin parts. Talking about medical implants, a lot of you must have heard about the hip joints, which are made from either PTFE or ultra high molecular weight polyethylene. Ultra high molecular weight polyethylene, as I mentioned earlier, is related to polyethylene, but it has only very high molecular weight, like 2 to 10 power 6 is the magnitude for the molecular weight. And this material has got very good wear characteristics, and that's what it is used for some components within the hip joints. So next category of high performance polymers is fluoropolymers. So here you can guess by the name that these are the polymers which would have presence of fluorine. A wide range of materials are made by choosing different kind of fluorine attached to different kind of backbone. So you can have the most common and the highest volume, most important fluoropolymer among all is PTFE. This is polytetrafluoroethylene. All of us know by the name of Teflon. So it has got, as I already mentioned about you, good dimensional stability and very high rate of, but its creep rate is very high, but it gives you very good thermal properties. You can use it from -180 degrees Celsius to as high as to 80 degrees Celsius. It has got good chemical resistance and electrical properties also. Then you have other polymers as well. So you have got FEP. So in this case, you have got a fluorinated ethylene and a propylene, where basically ethylene has been hydrogen has been replaced by fluorine on the ethylene and fluorine molecule, and they have been polymerized. So this gives it affects this kind of change affects its thermal stability to some extent. As you see, its range of higher temperature comes down, but it makes it more useful in terms of being able to be processed. So this becomes a more thermoplastic material as compared to PTFE. You can mold it into suitable product very easily. Similarly, you have got many other materials: PFA, AT, FE, ECTFE, PCTFE. In all of these, the key element remains the same: the presence of fluorine bond there to carbon, which gives it the very good chemical resistance, electrical properties, and thermal stability. Now, the if you look at the properties of these materials, because that's what is required to be able to find a suitable material, the way you change the chemical structure, again, it would have an impact on the properties. So these polymers, in generally, you don't use them for the mechanical strength. If you compare them with the other uh, high performance polymers, they will have much lower, these fluoropolymers have much lower tensile strength mechanical properties, but they have obviously they have one good property: they have their elongations would be higher, and they will offer you the chemical resistance and the thermal stability. Now, the moment you change, PTFE is the best polymer, as I mentioned earlier, has highest melting temperature. Once you start changing, replacing this or combining it with some other monomer, you lose on those thermal stability, and you can see the temperatures, melting temperatures going down further here. That also adds a value that other things can be processed by uh, processes where you can melt the material and you can shape them. On the other hand, this is something that cannot be done with PTFE. You cannot melt process PTFE. You have to take PTFE powder and fuse them, put them in a cold compression molding, apply pressure onto them, and then subsequently you have to put them in a furnace to fuse them together. So that's a longer process as compared to the other processes by which you can make other polymers into useful products. So one more thing that happens once you start playing with the structure, you start losing on the chemical compatibility also. So if you see wherever we have introduced ethylene or propylene kind of molecules, those polymers will have a lower chemical compatibility as compared to the fully fluorinated kind of materials. So that's a way, again, the structure is giving you different properties. PTFE is one of the material which has the lowest coefficient of friction, and that makes it very suitable material for many tribological applications. Yeah. Now, coming to the applications, they are used in the chemical industry to make many sealing kind of applications because of their chemical resistance and temperature applications, temperature properties. Good insulation properties make them good material for the insulation of wires and cables for electrical and electronic industry. You can see here. Then in automotive industry, they offer very good resistance to oils and many chemicals, so they are used as sealing material. One application of coating. So all of us must have used or come across our Teflon coated pan. We would have had at our home. So that Teflon is nothing else but a fluoropolymer known as PTFE. And this polymer, apart from being chemically resistant, highly thermal stable, it also has this property that it does not let anything stick to it. So that's why you can use very little oil and still be able to cook delicious dishes using this particular pan. Beyond this, fluoropolymers find wide applications in the field of medical field. They are used as polymer additives because they have got low coefficient of friction. So you add some of that as an additive to other polymers, nylons, PEEKs, and many more to reduce their coefficient of friction. Finally, they also go for semiconductor industry because a lot of times you use, again, very, very nasty kind of chemicals here. And similar same applies for the energy conversion and storage kind of energy storage kind of devices also. That's where also they offer the electrical properties combined with the chemical resistance, make them good material of choice. You also use in normal kind of applications also. So many times, even in the textile industry, in order to uh, make the fabrics stain repellent, some kind of coating is done onto them, which can involve some kind of fluoropolymers to them. Yeah. So these are the key applications of polymers. Again, we understand the properties and then you link them to the application. Going beyond, fluoropolymers are their cousins. You can call them fluoroelastomers. That key concept would remain same, that they will also have the carbon fluorine, but the difference would be all the things which we saw earlier. The fluoropolymers, they were linear, and these two materials which I have listed here, FKM and FFKM, are going to be cross-linked. Earlier ones were more PTFE. If you look at it, it's very highly crystalline because of its straight chain. On the other hand, these are the crossing material and they are going to be amorphous. And FKM and FFKM, both of them come from DuPont, and the difference between them is that one of them has got the fully fluorinated chain. So if you look, sorry, this is there's a mistake here. FKM has a partially fluorinated polymer chain, and the FFKM has got a fully fluorinated chain, and that offers, again, gives them the properties. So the one which has higher content of fluorine has better thermal stability and chemical resistance than the other one, but also it makes it costlier. So if you look at the prices of uh, conventional fluoropolymers and then fluoroelastomer and then perfluoroelastomers, the cost increased significantly. So because of these properties, they are used for very high performance sealing, and these seals are used in the field of aerospace, photovoltaic applications, industrial applications, oil and gas, semiconductor manufacturing, automotive, and chemical process industries. This is a special case study where the application of these special seals has been shown in the field of photovoltaic cell manufacturing. And this is a long process. The three aspects of this process: the wherever the we need to use very harsh chemicals, wet chemistry, and the HF, HNO3, etc., and alkaline bases also. Or you have very high temperatures, and that's where you have to have seals which should have very good compression set and force seal force retention. Or you have a plasma coming in contact with your sealing material. So these three different application areas were chosen from the photovoltaic cell manufacturing process, and different kind of seals were compared. Here you can see in the first application, wherever harsh chemicals are there, FKM and FFKM were compared. In this case, FFKM performed better. Again, we know why, because this will have a higher fluorine content. That's why it had better chemical stability. So there was not much change in the volumetric swelling of this material as compared to the FKM. Then this second application is weight loss upon the plasma erosion. So once plasma is the materials are exposed to plasma, they will have the impact on their properties, and then there will be weight loss. But that is observed very little in case of the fluoroelastomers, FFKM, as compared to the fluorosilicones and silicones. Once again, here the last application where the we are talking about the high temperature and comparing the sealing force retention. So that's where the fluoropolymers, sorry, perfluoroelastomer FFKM performs much better than the other sealing material. So that's how you break down the application into what kind of environment it is, what kind of requirements it is, and based on that you select a particular polymer for that. But these are the materials which are highly performing elastomers or rubbers, you can call them. And wherever you have very stakes are very high, that's where you don't worry about the cost, and then you choose these kind of materials. Coming to the next polymer, polyether amide. It's also a thermoplastic, amorphous thermoplastic similar to polysulfones, and it is sold by the name of Altem, which is from Sebic. And here now, by now you understand very easily that polyether amide, there will be an ether group and there are amide groups. That's how we are calling it polyether amide. It has very good good thermal resistance, and its TG is very, very high, 270 degrees Celsius. So if you remember what we discussed earlier, the mechanical properties start dropping once you cross TG. So you can expect that this material will retain its strength and stiffness up to 200 degrees Celsius. It also has very broad chemical resistance, dimensional stability, and also it is inherently flame retardant. So many cases, if you look at nylons, polyesters, and low commodity HDP, PP, those polymers are not inherently flame retardant. In order to make them flame retardant, flame proof, you have to add additives to them. You have to compound them with the right material to get the flame retardancy values. But some of these high performance polymers, they offer you don't have to do anything else. They are already inherently flame retardant. Being a thermoplastic, you can use all the methods which are used to mold it by melting and then solidifying. Yeah. Now, being a high heat resistant polymer, it's used for the internal components of microwave oven, because that's where temperatures can go high as 200 to 50 degrees Celsius. Also used for the electronic applications, automotives, aerospace, and transportation applications. I have again provided links here, so you can visit the sites to know more about these particular uh, polymers and their applications, and as most of them are from the respective manufacturers, they have got enough data available to quench any query you have about. Another specialty polymer is polyamide amide, sold by the name of Torlon PAI by Senesco. Senesco was formerly Solvay. Again, here you've got an amide group here. Sorry, you've got an amide group here and amide group here. So these two groups make it polyamide amide. This is as the information is provided by Senesco. It is one of the highest performing melt processable thermoplastic polymer, and it is also an amorphous polymer. It has got exceptional resistance to wearing, creep, and chemicals, and it can perform to as high as 260 degrees Celsius temperature. Very good electrical and structural characteristics. It maintains at high temperature because its heat stability is higher, and it has got very good dimensional stability and very low coefficient of friction, linear thermal expansion. So as a result of these properties, again further on the base polymer, there are some modifications done. You add the right kind of uh, reinforcing agent to it, and you can increase the strength further, and that's where high strength grades have been developed. So they perform just like metals at elevated temperature, and you can use them to make precision components, and they can be used for load bearing operations. And these high strength grades have glass fibers and carbon fibers filled in them. Apart from these high strength grades, you can use it for wear resistant applications also. In this case, I believe that they would be combined with suitable tribological additives which will reduce their friction and improve the wear characteristics. And so having additional benefit of this tribological property over the chemical resistance and thermal stability would make them very good material for certain applications. And being a high performance polymer, it goes for aircraft, semiconductor, and oil, gas, electrical, and automotive industries. So you can make different kind of components using these materials. Let's go to slightly simpler specialty polymer as compared to the earlier ones, polyamide. This time we don't have to worry about two, only amide structures are there, amide functional groups are there. But this is again a very special polymer because it works at a much higher rate than any other polymer, even higher than PTFE. So if you look at the temperature range that is provided, it can go from minus 196 degrees Celsius, that is the cryogenic conditions, to very high temperatures of 288 degrees Celsius, where you can use it. And for short duration, you can go as high as 482 degrees Celsius temperatures. On top of that, you can combine it with suitable reinforcing agents, and that the temperature range also goes further. Now, the polyamide is sold by many manufacturers. I have listed two of them here. One is Mitsui. Mitsui's products are branded name and Aurum, and DuPont has uh, polyamide available in two different forms. One is in the form of parts and shapes, where you have these rods, plates, and all available, and you can take them and machine them into the kind of product you want to use. They also have films for some other kind of applications. Now, I have highlighted two key applications of polyamide. Polyamide is again very costly material and not to be used very for to change any other material. But temperature where the pressures are very high, you need very high temperature on wide range of temperature. That's where they are used as seats. So these are the seats for these ball valves, where you can use them for these applications, because they have very high creep resistance also and good wear properties also. So that's one industrial application area where polyamide is used widely. Apart from that, it is used to replace metal in aerospace industry. So in aerospace industry, weight is a challenge, and if you use metals which are heavier for any job, then you are going to increase the overall weight of the your vehicle, which would have negative implications. So for that, you want to replace metals and with lighter materials, but they should be able to perform under the high temperatures with which which metals can take very easily. So one example is aircraft engines, and that's where the temperatures can go from as low as minus 54 degrees Celsius to 343 degrees Celsius, and that's where you have to use these fasteners or clamps in place. And what I understand, there's a lot of vibration is there, and that vibration, and not everything, every polymer, the polymer works along with the vibration as well as the temperature, extreme temperatures. So that's where polyamides have been used. They have been found benefits of replacing stainless steel and aluminum with polyamide based clamps. So this is one niche application of polyamide. Coming to one of the last application, sorry, not last application, the last polymer, that is the polybenzyimidazole. And polybenzyimidazole is called again one of the world's highest performing polymers. And there are reasons for it. So first of all, it's very very unique and niche kind of material. There's only one company, as per their own website, PBI. That's the only one commercial manufacturer of PBI based fibers and other products. And it's polybenzimidazole. You've got benzene and imidazole kind of structure is there. So this material is available in the form of powder, solution, and compound and film and fiber form from PBI. We can take pride that our own Garda Chemicals from India has also developed their own form on product of polybenzimidazole. They call it ABPBI. The difference is that the PBI, that is the way PBI makes stelazole, they use two different monomers with functionalities. So if you look at this monomer 1, which has got two hydroxyl groups, and this other one has got two amines. So this is A type monomer and this is B type monomer. On the other hand, what Garda Chemicals have done uniquely, they have clubbed these together in one molecule. So you have got amines and you have got carboxylic acid. So A and B type functional groups are available on the same molecule, and which can be polymerized to get the final polymer, so ABPBI. Now, this is one of those type of polymers which is fully aromatic, and it's a heterocyclic polymer because you can see presence of nitrogen in the chain. It has got very good mechanical properties, very good thermochemical property stabilities. Its TG, the glass transition temperature, is high. It's as high as 430 degrees Celsius. And it's reported that melting temperature is as high as 600 degrees Celsius, making it very, very high performing polymers. So this one again is inherently flame retardant polymer. And it goes for a wide range of applications: industrial, semiconductor, petrochemical, chemical, aerospace, and used for coatings also, and then fuel cell membranes also. So the two applications which you can so this material was developed actually for very high applications, keeping in mind so there was an accident in Apollo mission, and because of that, not having the right kind of gear, the people who were inside the ship were they perished. So that's how this material was developed, and it goes for the development of suits for the astronauts. The NASA uses it, and it's very regulated material which is not sold very easily elsewhere. It's also used for other application where lives are at stake. That's the firefighting job. So here, the outer shell of these very high quality firefighting suits are made from PBI and polyaramid. PBI still does not have very good properties to make a fabric. That's why it's blended with polypara-aramid, what we saw earlier, and then 40-60 ratio is used to make this kind of protective gear. I'll just run a small video for 2 minutes to tell you about how PBI works. I'll switch a window, 1 second. Can you see a YouTube window?
Yes, sir.
Okay. So that was the video I wanted to show you about PBI, how it is used, and that was the last slide. And now I move to the summarizing my session. So overall, what I wanted to convey in this presentation was that the high performance polymers, they are not produced in very large volumes, and they are not very cheap. They are very high cost polymers, and but they are the go-to material if you have any extremely demanding conditions such as extreme temperature or exposure to high chemicals. Second part that what I wanted, second point that I wanted to make, and I stressed upon it many times, that you understand the chemical structure and the properties of the polymer. They are linked together, and then that understanding has to be very very clear to be able to screen different materials for different applications. And as I mentioned in many times, there are different applications which are listed here: aerospace, medical, automotive, pharmaceuticals, and new energy kind of applications. That's where these materials are very widely used. So that was overall my the what I wanted to share with you about high performance polymers. It's a very vast area. It was very difficult to either cover. It could have been broken either one polymer and looking at all the applications where it goes, or looking at one application area and going through all the polymers. But I wanted to give you a flavor of different polymers, their capabilities, and different areas also. So that's the way I had structured it. Hope you found it useful to some extent. Links are provided. I hope you will get access to this presentation, and do visit those links to know wherever you have any doubts about of these uh, any of these applications or polymers. So if you have any questions, I will be happy to answer those questions.
Participants can unmute the mic and get the
Participants can unmute their mic and ask the questions.
Hello, sir. Can I ask the question?
Yes.
Yes, sir, please.
Sir, nowadays, as we are now just going through the performance of polymers session, so as at the end you had shown the video regarding the polymers which are used in clothes, right? So nowadays, these are used very tremendously and are growing in a very much manner. So, as we are going through the development, we are seeing that Chinese military has also introduced one kind of a polymer cloth by which the person can't be seen. So, there, which kind of polymer is used?
So I have read some kind of news about this. Unfortunately, I have not been able to look into it to understand what kind of polymers it is. But I would expect
Okay.
it has to be some kind of light bending kind of either it has to be light bending kind of phenomena that polymer has to have, where it can bend light in such a way that you can, when you are facing towards something, the light would
Okay.
coming from that particle, that object would not come to your eyes, but what is behind that, it will come from that.
Okay.
That's one aspect. Or it could be something that can completely
So,
black out things. It can completely absorb the light, so nothing gets reflected. So those two aspects could be there. I'll have to look into this, but very interesting example.
means can we make such kind of polymer cloths?
Certainly, we need to understand the right polymer, what kind of polymer it is, and that's the material part of it, and then get it in the right kind of, the refractive index or the optical properties in this case
Yeah.
would be
Yes.
required.
Yes.
Then comes the making the fabric part of it, what kind of method you use, to what kind of weave you do, what kind of fibers or linear diameter you use to
Alright.
make the right kind of
Okay. Yes, sir, yes, sir. So my second question is that whenever means it is also related to defense. So most of the vest means the jacket,
yeah.
VEST. Most of the vests which are being used in for protective of a body. So in that, which kind of polymers are used? Because as we can see that if a bullet is fired to the vest or to the bulletproof vest, it gets actually bend. It bends the tip of the bullet and it does not penetrate. So there,
Yeah.
which kind of a polymer can be used or which is used?
So two polymers are used for this application. One is the Kevlar, what I mentioned earlier. Kevlar has got those ballistic properties. It is very cut resistant. That's one
Yeah.
application.
Huh?
And so jacket is again not just a simple cloth like the kind of any shirt or t-shirt you wear. It also has
Right, right.
multiple components. So there'll be fabric part of it, which would contain the Kevlar and Kevlar based cloth. And then you will also have
I think
plates.
it is a combination.
Yeah, it's a combination. So you'll have inside that
Com-
you'll have the plates as well, which can be made from ultra high molecular polyethylene, or you could have some kind of,
Composites.
yeah, that kind of material.
Okay, okay. Okay, okay, sir. Yes, sir. Thank you, sir.
Thank
From
you.
my side, it is okay.
Anyone else? Sir, I would like to ask one question.
Yes.
How to take a golden mean between easy processing and to maintain the mechanical properties, especially strength, particularly polymers, we face this problem. So it should be easy processing, easy melt, and also have good mechanical properties.
So could you please repeat your question? Sorry, I missed it in between.
Mean, because we try to we know that when we try to go for the easy processing means to lower the TG, whatever the crosslinks and the the things what blends we have to add, then the strength will hamper.
Right. So neat polymers are not used all the time, right? So you always try to use suitable processing aids, suitable additives or fillers in them to get either desired kind of look. You want to color them, you want to improve their strength, you want to add some other properties, combine some properties which are not there. So that's the one way by which you can take any basic polymer and add suitable filler additive to it and improve its properties. Now, challenge is that if you want to have very high properties, you have to have materials which polymers which are very high molecular weight, or they have very good secondary interaction bonds, hydrogen bonding, sorry, or the polar kind of groups in them. But that makes it challenging because the viscosity will also be higher. So always it's a balance. So the complexities in complexities in the processing as well as the polymer structure, both of them would increase the cost up. Now, the kind of application you're looking at, whether that can absorb that cost or not, would also have to be factored beyond the properties of the polymer and processing also. So these three factors together and in combination with suitable kind of additives, fillers, would give you the right material for any application. I hope I was able to address your question.
Yes, sir. Thank you. There are two hands are raised from Sanjeev Zamge and Ritesh Mulge. So, do you want to ask the question? Ritesh
Yes,
Mulge,
sir. Yes, sir. Sir, whatever the
please.
things you are bringing the changes in the property or the compound, how are compound has got formed? Is there any there's on technical? I mean, how are you ensuring that particular compound has formed, sir, in this one?
Could you please elaborate your question? How
Yeah, yeah.
particular compound has
No,
formed means?
yeah. Whatever the changes you are bringing in each of the things that you have quoted, sir. So you are changing the chemical compound. How are you ensuring that that particular chemical compound has formed or not? How are you going to ensure that, sir? That is very basic. Layman question that I'm
Characterization.
asking. Yeah. Correct.
Okay,
Sir, he's asking, I think, about characterization.
Yeah.
okay. So uh, in lab, it's a very different way the way it works in lab. In lab you can use characterization tools to identify an unknown material, and sometimes you want to mimic something that your competition has done. In that case you do reverse engineering, you get some material, you study it by different techniques, you do FTIR analysis, TGA, DSC for it, you try to dissolve it in different solvents, you can extract what kind of additives it has. You burn it and then see the ash content. So those are the studies by which you can try to identify an unknown compound, and that's a very basic uh, reverse engineering technique that is used across industries. So that's one way. On the other hand, when you have identified based on your desktop study, based on your knowledge, what kind of material is used, you reach out to the right kind of supplier for that particular grade, and they also support you in developing and selecting the right material which could be suitable for your application. So those are the two approaches which are adopted generally to select the right material.
I hope Ritesh ji, you got your answer.
Yes, sir. Yes, sir.
Zamge sir, Zamge sir, are you interested? Okay, anyone else? So let us wrap up
Sir,
this session. Yes, sir. Yes, sir. Yes,
in
sir.
case of Kevlar, that is para aramid, and in case of Nomex, it is a meta aramid. So the properties are quite different. Suppose
Yes,
if
sir.
you make a mixture of para meta, that means taking the meta diacid and taking the paradiamine, that new polymer has been reported earlier or not yet?
I have not come across it so far. What has been commercialized are these two,
Yeah,
and
that
they
is
are
good.
available again in different grades.
Yeah,
So,
we can make 50-50 also, but I
yeah,
thought that maybe we can make
correct.
more
Theoretically,
amorphous,
yeah,
more amorphous.
theoretically, yes, sir.
And the second question, sir, I would like to ask if you are allow me to ask that.
Yes, sir.
Sir, in case of PBI, we have got very high glass line temperatures, like 430 degrees centigrade, and very high melting temperature, like 600 degrees centigrade. So, how these polymers are processed actually into the form of fibers?
So, sir, they are the way the PBI itself is made is having a reaction medium as polyphosphoric acid.
Yeah,
So that's
PPA.
one chemical,
Yeah,
phosphoric acid, which
yeah,
can
PPA.
dissolve the polymer also. So that's the way processing is done. You take conventional process of solvent spinning or solvent casting. That's kind of process you can use to convert polymer to suitable products.
Yeah, thank you very much, sir. So I was just thinking, instead of the polyphosphoric acid, can you use some other solvent in which the PBI can be made soluble?
So again, it will be instead of choosing solvent A, solvent B, but
Hmm.
again the process is going to be a similar process, a solvent based process.
Okay, thank you
And
very
I
much.
think what they do, so there will be two steps. So what solvent is used to dissolve your monomers is polyphosphoric acid, where you can dissolve it and then you can get a solution of the polymer. So you don't have
Okay.
to solidify it again, like, and then again dissolve it, so that you cut down on the step.
I have come across some polymers actually of PBI,
Okay.
wherein they have made bulky group substitutions
Yeah.
and thereby large volumes,
Hmm.
and they made it soluble in conventional polar aprotic solvents.
Okay.
Yeah,
So
so that
yeah,
was actually useful.
yeah, that will be very good application, because if I'm not wrong, this polymer is as costly as I think $200 per
Yeah,
kg.
that is
That's the
true.
kind of price it has got.
No, this type of polymers were developed for the Vikram Sarabhai Space Research Center.
Yes, sir. Yeah,
Thank you very much.
yeah. Thank you.
Okay, so shall we end the session? Thank you, sir.
Thank
If
you,
there
Mr.
are
Dr. Patil.
no any questions from the participant side, uh, thank you very much, sir. Dr. Neelesh Shukla ji, you have elaborated right from the basics of polymer, different varieties of polymer and their versatile applications, and also a beautiful video of PBI, which participants might have understood the varieties and without polymer, we how the polymers are important in daily life, each and every field of day-to-day life. We have to use the polymers. So very interactive and informative session you have conducted. So on the behalf of our college and our trust and AICT ATAL, I thank you very much, sir, for accepting our invitation and delivering such a nice session, sir. Thank you very much.
Thank you, Dr. Patil. It's a great pleasure to be able to present the topic I love a lot. And I would say that I am not sure whether anyone else learned anything from this or not, or they already knew to a higher level. But certainly, while preparing for the presentation, I came across many new concepts and many new information that I was not aware of earlier. So that has been good learning for me. So that has been very beneficial for me. And moreover, the questions from which I learned about new developments taking place in China, that's also a very good takeaway for me. So thank you very much for this opportunity and adding value to my
And,
professional knowledge as well. Thank you.
and also I would like to thank Professor Maldar sir for making this session interactive and his guiding words. Thank you, sir. So I request all the participants to
Thank
fill
you.
the feedback form, given it in the chat box. Thank you, sir.
Thank you.
And fill up the
Can I leave?
feedback form as early as possible. Yes, sir. Thank you very much once again. Good night,
Thank
sir.
you.
Good night.
Good night.
Yeah.
Bye.
Thank you. So I will hold the meeting for some while for feedback. A link is there.